Oh, hi, good morning. Good morning, let's get started. Hope everyone had a good weekend. Right. Hope everyone had a good weekend. It's Junior Parents Weekend. So we'll have the midterm on Wednesday, right? And it'll basically cover this module, but that doesn't mean that you can forget the previous one. So it's always hanging in there. If you have any questions about the midterm, talk to me after class. I would set the exams here, but basically trying to be similar to the last time, make it a little bit easier by, I'm thinking of making it into a true, false, or no answer kind of model, right? So you get to answer one or the other. If you get it wrong, then you lose points. If you don't answer, then you don't lose or gain. But if you get it right, you gain kind of stuff. Let's see how that goes, right? So, do you have any questions about what we covered so far in terms of process synchronization, and how is the programming assignment coming along? Good. Okay. So we can continue on with the deadlock avoidance algorithm. Yes.
What is the
there's still more in the front, but so we were looking at the problem of deadlock last class. You know, the 4 conditions which have to hold all the time. So then we were looking at ways to prevent deadlock by trying to make sure that one of those conditions don't happen. Right. The other alternative is to do a deadlock avoidance, where you make sure that deadlock can never happen. Not that it's imminent, but it can never happen, right? So we define. So in this class, we'll see we define a notion of a safe state, unsafe state, and just because you're in an unsafe state does not mean that you have to go to deadlock. But deadlock is a condition, the special case of unsafe state, right? And deadlock avoidance tries to make sure that deadlock can never happen. So in the simplest case, you need to first tell the OS all the resources that you want, and you can run some algorithms to figure out if deadlock is ever possible with the number of requests that you ask, right? And again, with the requests that you have, you may go to deadlock, or you may just be in unsafe state, right? So just doing that and making a static decision before your program starts would throw many of the conditions which are more useful. And so the more normal thing that you can do is you say upfront what you want, and before the system lets you proceed, get new set of resources, you figure out if there's a possible way for you to finish, right? If there's no possible way for the processor to finish, then it won't let you go, right? It doesn't matter whether that possibility may or may not be what the actual program takes. So you look at all the possible states of resource allocation in the future based on what you have and what you have asked for, and if there is any possible way that the system can make progress, you let them go. Otherwise, you don't let them proceed. And so for that to proceed, we need to have a notion of a safe state and an unsafe state. So safe state you define as, so you have a bunch of processors, and you have a bunch of requests that each process would make during its lifetime, right? So a safe state is if there exists a sequence of scheduling processes where each process can get all the resources that it wants from that point on, right? If there is such a path to completion, then that's a safe state. So it does not mean that all the resources have to be available. So it does not worry about starvation. So if there is, if it means that one path that you have to take would mean that some other process has to finish and then you have to proceed, that's fine, right? It only talks about a possibility, not the case of starvation. So some process may have to wait while the other processes finish, right? And in the next slides, we'll see examples of how these things will happen, right? So The basic fact is in a safe state, deadlock is not possible. In an unsafe state, deadlock may be possible, but deadlock need not happen. So you can be in an unsafe state and still not be deadlocked. So the figure that your book has is sort of like this. So if you're in a safe state, deadlock is not possible. If you're in an unsafe state, unless you take precaution, you could go into the deadlock state, right? And I have to stress again that just because you're in an unsafe state does not mean that you have to go to a deadlock state. But all the deadlock prevention and the deadlock avoidance tries to avoid you from going to deadlock state, not necessarily go from deadlock, from the unsafe to the deadlock state, right? So they are more conservative than they have to be, because you don't know when you're going from unsafe to the deadlock state. So, so we define a notion of a resource. So the problem now is to figure out how you can do this in the operating system. So the operating system has to have a notion of what resources are allocated to what process and how it can deal with the figure out when this deadlock is when you're going to go into an unsafe state. So so we do the notion of a resource allocation graph. Resource allocation graph is very similar to the the graph we saw before. I forget the name of the graph, right? So basically, we augment the graph to say if a process would request a resource, right? You leave a claim graph, which is basically a dotted line, right? But in the graph we looked at before, if a process is not having a resource, then there is no edge. Here, if a process could potentially request an object, you leave a dotted line, and if a process is allocated a resource, then you leave it as a straight line like before. So this is the sort of stuff we had before. So over here, process P1 has R1, P2 is requesting R1, right? These two dotted lines means that P1 could request R2 at some point, and P1 can request R2 at some point. So that's the only augmentation you do. So basically, you're saying that P1 and P2 may request R2 at some point, not at this point, right? So if P2 was assigned to R2, right, then potentially you're entering a unsafe state, because P1 could request R2 at some point, right? Because there's a claim edge which says that P1 would be interested in R2 at some point. So if this R2 was allocated to P2, right, at this point you're entering an unsafe state. You're not entering a deadlock because there's no circular weight at this point, right? But if in the future P1 requests R2, at that instance you'll get a deadlock, right? So there is no deadlock at this point, but if you allow this transaction to go through, then you're entering an unsafe state. So potentially in the future, if P1 requests R2, you will enter a deadlock, right? But all this graph says is P1 may request R2 in the future, and usually you learn that either by P1 stating upfront what it needs, right? And the P1 may actually never actually want this resource, right? So all this is based on the fact that it's very hard to processes to say exactly what they want, and processes give up resources, right? So if you have a long process, and for the initial half it uses a tape drive, and the final half it uses a printer, right? So if R2 happens to be a tape drive, then the process may never actually use it because it's used all the R2 that it wants upfront, and it only needs a printer to finish, right? So that's the important part to remember. That kind of sort of goes to some of the issue that you brought up, right? You can only guess that what it may need in the future. So you would have to prevent this from happening. You would have to prevent this potential entry into an unsafe state, even though it may never get into deadlock. But if you want to avoid deadlock, this has to be avoided. So the previous graph approach works if there's only one resource. But if you have multiple resources for R1 or R2, then that approach does not work. So the other example is, it's more theoretical algorithm which does not work in practice because it's you have to know the future, is called the banker's algorithm, right? Dijkstra designed it, and essentially the idea is it's supposed to model how a banker would work. So banker gives you credit lines, right? The bank gives you credit lines, and with the assumption that if you ever exercise your credit line, right, then the bank should be able to give you the money that it promised, right? But the banks do not have to have the sum total of all the credit lines for it to give you a credit line, right? So if there are 10 people and each one of them it gives a credit line of 10,000, the bank does not need 10 times 10,000 to be in business, right? The assumption is not everybody maxes out the credit card all the time, and people repay, right? So they use an algorithm where they would let you borrow money if they know that they can eventually satisfy every customer what they promised, right? Not how long it takes. Typical banks don't do that because they have so much money that you hardly notice this is happening, right? So they want to make sure that if everybody comes and asks them in certain order, they can still give them all the money that they promised, just not immediately, right? So if there's any way that they can give you the money, then they'll give you. If there's no way they can do that, then they have to not give you. And in the bank case, that's a bad thing, right? So if they promised you a credit line, then there has to be some way for them to give it to you, not immediately, but at some point. It depends on the fact that people return the money back to the bank, right? So it's fairly easy to see that the one request cannot be more than what the bank has, right? So if the credit line, if the bank gives you a credit line of 10,000, if the money it had was 20,000, this algorithm can never work because it can never give the money to that one person, right? So it's a way for the banks to play with the money that they have in order to satisfy a whole bunch of users, right? Where it gets into deadlock where it promised more money to somebody, but then it's not able to give the money to them, right? And so that's supposed to be how the bankers work, and I'm sure that's how they still work. But when the banks have trillions of dollars, your credit cards, you rarely wait for your credit limit to be released by somebody else. Okay? But the banks never actually have all the money that they promised to others. Right? So we try to implement that. So basically, if you look at the analogy, if you look at the currency as the number of resources, right? It's sort of trying to figure out that you don't want to get into a state where you cannot service all the clients. So you have a data structure which has a large number of arrays and stuff, right? The idea behind this algorithm, right, is every process when it comes in gives a list of resources that it wants and the number of resources of each kind, right? So upfront you say what is the maximum amount of resources that you would possibly want, and you put that in the max array, right? And then you maintain a list of all the resources that were allocated to different processes. And then you maintain a list of all the resources that your process would want, which is basically subtracting the max from what you have. So when you come in, you say how much you want, and when you are assigned something, you keep track of how much was assigned to you, so you know how much you need in the future. The crux of the algorithm is you figure out if you ask for a new set of resources, right? You look at all possible cases of allocation of resources for the available resources to see if there is any possible way for your resource to be satisfied, to be in a safe state, right? So we define what a safe state is. So if there is any possible way, then I let the allocation go through. If there's no possible state, then the allocation cannot proceed, right? So that's the idea behind this algorithm, right? So at every step, so before you start, you ask how much you want, and then at any one step, I know how much you have, I know how much you would need. So if you ask something, I have to see, given all the allocations which are out there, and given all the stuff that you have and given how much you want, whether I can make progress, whether some sequence of processes can finish where each process could get all the maximum that it could possibly want. Right? Once you allocate it to it, it'll finish and then it'll return the resources back to you, and eventually you can find a path where all the processes can finish. If there exists one of those, then you let the allocation go through. If there exists none, then the allocation does not go through. Right? So before I go into the algorithm, right? How often would you have to run this? Is it okay if you run it up on the front, right? When I do a static allocation, is it okay? Or do I have to run it more often? If I have to run it more often, why do I have to run it more often? Can this be run up front, and if it was okay up front, can we proceed? Yes.
What exactly do you mean up front? Like whenever?
When I start out.
Oh, well, wouldn't that be whenever?
So when I start out, I would have asked for the maximum resources, and the list of resources allocated to me is 0, right? And at that state, you would run this algorithm to see if, essentially, the same algorithm, right? But when you come in, you ask for the certain number of resources. This allocated to you is 0, right? And the system runs the algorithm, and it should figure out that there is a possible path for you to finish, right? What it does. So at that point, there is a possibility way for it to finish, right? So is that good enough? Can you just let the processes go and not having to do this later, right? Yes.
We usually run it almost continuously, or at least pretty often, so that when some process is returned, you take that back into the calculation. If you stop it at one point, you might end up with a situation that's won't allow other processes to wait in the future.
So why do you think it happens? Why does it happen that? Why is it like, since it was good when you came in, why do you have to change it afterwards?
Well, it might be good for one process, but if other processes want to come in at another point where the other process is running, you want to get the most current.
But if you do this for all the processes, right? All the processes, when they come in, they have to do this stuff, right? Why wouldn't just doing it up front not work? I think you have the answer. I think.
I'm trying to figure what you said.
The answer is in the banker's algorithm rationale, right? So if I come up front and if I run the algorithm to see if there are all possible cases, right? You are still considering the fact that the others will release the processes and stuff, right? If I just only run it on the case where I just mentioned, where you only run it up front and figure out if there's any possible way and stuff, and not assume that anything will be returned, right? Then you have to go into the very extremely conservative case where I have to assume that none of the things will be returned back to the system, right? So I can only give enough resources that anybody could possibly want at all, right? So it degenerates to a case where the simplest case, right? The whole point of the banker's algorithm is somebody would return stuff in the future, so you would have to essentially run it every time that a resource is allocated, because based on what was allocated, right, we could potentially go into an unsafe state, right? So the list of allocations can be at sort of such a point that no one process can return at that point on, right? And it goes to the nature of how the banker's algorithm work, right? If you want to change it and run it only once, then you have to essentially be extremely conservative and only give resources that you could possibly want to use, and it could be faster and not exactly what you want. So these algorithms try to let you make progress and let you go to a state where you could potentially enter an unsafe state and then back off, right? So the assumption is it gives you better performance, right? So I'm not going to go to the exact line by line of what happens. So So essentially, let's go back to the previous slide. So you have n processes and m resources, right? So you maintain a list. You maintain a vector array of length m, which is the number of resources called available, which says how much of the resources are available for each of the resource. So if there are m resources, you'll keep a count of how many of each resource is still available. You keep a list of max, which is the amount of resources that each process would request of that particular resource, right? So for resource 1, if process 2 wants 4, the corresponding entry would have 4. The allocation states how much of it was actually allocated to a process, and need says how much you would want to complete the execution. And essentially need is max minus allocation, right? So the way the algorithm works, when I ask for a new request, right, I set all the processes which haven't still finished. I set all the processes to false, right, saying that they haven't finished. Then we try to find a set of sequence such that you can finish a process, change the state of the process to of any one process to true, and try to find the set of the all the possibilities for it to finish, assuming that all the processes that were finished before it would finish and then release the resources, right? And you find a state like that, right? Does that make sense? So I take the first process, assume it's finished, right? And then assume that this resource will be available to the future one. So you take a second process number 2 and see if it can finish if the previous one would have finished and returned its resources, and if you add it to it, and then you can make progress, right? You have to do this for all possible combinations of the process. So it's a very expensive operation. The operation of finding out whether it's a safe state, and this whole operation should take its order of m times n squared, right? So is that clear? The higher level of how these things work. You take each process, right? So it's a permutation combination of all the processes. You take each process, assume it's finished, right? And then take the next process and see if the first process would have finished, returned all its resources, and if you use that, you can finish, right, in the same state. And then you move on to the next one. So you take the third one, assuming that 1 and 2 finished, and then see if the third will finish. And if you take fourth one, assume that 1 and 2 and 3 would finish, and then you do the fourth one, right? And then you change the order in which you are choosing this 1, 2, and 3. So if there exists any one combination which can follow this one, then it will finish, right? The explanation is kind of long because the operation is, so you're doing all possible combinations. So if you look at the algorithm perspective, right, this is exponential algorithm, right? It increases with the number of processes and number of resources in the of n order of m times n squared, right? So actually, I explained both of these together with one slide. The first one is trying to figure out if it's a safe passage, and the second one is trying to figure out the allocation I just mentioned. Right? You take one process and see if there's a safe state. Take the next process, and so on. If one path like that exists, then it's considered to be safely allocated. And what it essentially means is there is one path. We're not worried about starvation at all, right? So it may mean that the safe path may mean that process 0 has to finish, then process 1 has to finish, then process 3 has to finish. So process 4, which comes after those, would have to wait for a long time, right? So we have one small example to help make these things more concrete. I'm still not going to go through the safety check because that's again expensive operation. You can learn through it, right? So here we have 5 processors, P0 to P4, and so we have 3 resource types, A, B, and C, right? And there are 10 of A, 5 of B, and 7 of C. So at one time point, this is what we have, right? So it says that the process 0 has 0, 1, 0, meaning it has 1 of B resource and no of A and no of B. The maximum it wanted was 7, 5, and 3, right? And the available is A, B, and C, right? And sorry, the available is 3, 3, and 2, right? So at this instant, for process 0, it wanted 7, 5, and 3. So it would potentially need 7 of A, 4 of B, and 3 of C to complete, right? And so on, right? So if P0 was to come in right now and ask for all its resources, then it cannot get all the resources because the available resources is only 3, 3, and 2, right? Right? So this is only allowable if there exists a way for other processes to finish and returning their resources so that if P0 was to ask that, it can make progress, right? So this is the need matrix, right? The need for, so it's basically the max minus allocation. The need for P0 is it wants 7, 4, and 3, and so on. And if you go back to the available thing, right? The availability is only 3, 3, and 2. So at this point, P0 cannot request all it wanted. P1 can request all it wanted because it only requests 1, 1, and 2, and the resources you have is 3, 3, and 2, right? The system is in a safe state if you ran through the system, the safety algorithm, which tries to figure out all possible combinations of the processes where one of them can finish and return the resources and stuff. So the algorithm, if you run it, that's one of the safe state, right? The P1, P3, so P1, P3, P4, P2, P0, right? So essentially, at this point, right, if first P1 finishes, right, P1 will finish only after it gets its maximum allocation. So it right now it has 2 and 2, 0, 0, right? But it really wanted 3, 2, 2. So you would allocate the available resources to P1, right? So when P1 fully finishes, what would the available be? So what would the available resources be after P1 finishes? Right? So essentially so P1 right now has 2 resources, so it will have to be allocated all it wanted, but when it finishes, you will have 5, 3, 2, right? So when P3 finishes, right? So at this point, if you stop everything and then let P3 finish, what would the sequence be? Yes.
7, 4, 3.
Yes. And so on, right? So it's 7, 4, 3, and if you do P4, right? Right, and then P2 would be so P0 can get all the resource points, right? So essentially, there is one particular way of making this happen, right? So if P0 comes in right now and wants to get all its stuff and finishes, you can't allocate P0 right now, right? But if you wait long enough in the future, P1 has to be scheduled next, P2, P3, P4. They have to be let go. I mean, they have to let run. They have to release all the resources. And if you go with this sequence of events, then eventually P0 can get all the resources that it wants and can finish, right? So right now the state that you are in is safe state because there exists one of those. There exists a sequence, right? And the operation of finding out this P1, P3, P4, P2, P0, this sequence, right? That's the banker's algorithm tries to find that, right? So when the algorithm is running, it may find that this sequence, right, is not safe, right? This sequence cannot happen. I'm not sure, but basically you're trying all the sequences, right? So you're trying for all possible combinations of the processes that exist in one sequence. So the so if you request, if a process requests 102 at this point, right? I think it's P0 is requesting 102, then you can again do the similar stuff that we did, and for that the sequence is P1, P3, P4, P0, P2, right? So if a different request comes in, then the set of operations are different based on, so it essentially says that if it gives that 102 to one process, what is the sequence which has to happen in the future to make it stay at a safe state? So the allocation decision is based on trying to see if I were to give this resource to you, would I be able to finish, right? What we're looking at here is, with the stuff we have, can we finish? And here, if I were to give this to you, would I finish? If it is true, then the allocation happens. If it's not true, then the allocation cannot happen, right? So similarly, can the request 330 by P4 be granted? So after the request 102 goes through, right? This is how the state changes. Essentially, the available state now goes from 332 to 230, right? Let's go back to that. So P1 now has, actually P1 requested the resource. So P1 now has 302, right? P1 previously had 200, so now it asks for 102, so now it has 302, right? So the available resources are now 2, 3, and 0. So the first question, can if P4 requests 330, can that be granted? I see people nodding. Why? Yeah, it's actually easier, right? There's only the available resources is 2, 3, and 0, right? So you can't give 3, 3, and 0, right? So the next resource, can you allocate 0, 2, 0 to P0, right? That could be allocated by the first check, but then you have to run the algorithm to see if there's a safe state, right? And if you find one sequence which can make this happen, then you can let it go through. Otherwise, you can't let it go, right? So I seem to have lost a whole bunch of people, but right? So at least the takeaway message is, trying to figure out whether the system enters into a deadlock, whether the system will enter into a deadlock. It's not a trivial thing, right? If it's hard for us to understand off the top of the head, for the OS to do it on the fly is not a trivial task, right? And we are talking about an algorithm which actually tells you precisely how much resources that it wants upfront, right? It's easy for the operating system to keep track of what was assigned to you. It's much harder for the operating system to know what you would want in the future. So for an algorithm which says that I know precisely how much you would want at any point, right? And it's easy to maintain how much you have right now, and for the OS to maintain how much resources it will have in the whole system, right? Every time it has to allocate a resource, it has to run this algorithm, right? If you don't run it every time, then you could potentially be in a state where you gave resources and you could be in an unsafe state. And running this algorithm is O of, again, m times n squared, which from the algorithm perspective is bad, right? Because it's actually an exponential algorithm. So when you increase the number of processes or increase the number of resources, then the running time goes high exponentially, right? So that's one of the reasons why you don't want to do this unless you're forced to do it, right? So for the OS, it's easier for it to say, I don't want to deal with it because it's a complicated process. So unless this algorithm comes back and finds one sequence where the resource allocation can proceed, it has to deny it, right? And that's the reason why many of them don't try to do that, right? Yes?
Can you just go back to a second? So that 230 available, that's just initially the resources that you have, and therefore you can only satisfy the need for P1, and that's why you start there.
So right now we have 2 of A, 3 of B, and 0 of C, right? So depending on who comes and asks, right? So the first one is a little trivial because you are asking if P4 comes in and asks for 3, 3, and 0, then upfront you can't say anything, right? But you could. So right now, any one of them can come and ask anything they want, right? So like the 0. 020, right? Or 010. Any one of them can make a request, right? So when they make a request, you have to see if simple cases whether we have enough available resources. If you do, then you have to see if there's a sequence where you can still make progress. Does that answer your question?
And then if you can, then you add the allocation to what you have available?
If you can, then you give that resource. So if somebody asks for 020, like if P0 asks for 020, and if you found one sequence, then you give that resource to P0, which means that allocation for P0 will go from 010 to 030, and available will go from 230 to 210, right? So you're in one state, then you proceed. And then if somebody else comes in the future and wants more resources, and at this point, if one of the processes completes, right, if P1 completes, then it'll return all it has back to the available, right? So available is a global data structure which keeps track of how much of each resource is available. And yeah, it'll change state whenever you request for a resource or when you exit and release the resources, right? Yeah, so this is one of the chapters I would read carefully in the textbook, right? So the essential idea is what I talked about, but the details of working through it through an example might help, right? And the algorithm basically tries to figure out how this thing happens. So magically, here I'm saying P1, P3, P4, P0, P2 would work, right? The algorithm tries to figure out by saying, starting with P0, let's assume P0, P1, P2, P3, P4, and then P0, P1, P2, P3, change the permutation combination till you find one sequence, right? And that sequence keeps changing depending on what your state is. So if you look at the previous case, at this stage, P1, P3, P4, P2, P0 are the one up here worked, right? But if you allocate 102 to P1, right, then the safe state changes, right? So at that point, the safe execution is for P1, P3, P4, and so on, right? So it depends on what was allocated and what was asked. Right? So then we look at deadlock detection and recovery state, right? So the first two things we looked at was deadlock prevention and deadlock avoidance. Tries to make sure the deadlock never happens, right? So the next approach is let deadlock happen, and when deadlock happens, try to detect from it and try to recover from it or deal with it, right? So the way we do detection is through what we call a wait for graph, which basically takes the state graph we have before and changes some of the edges to processes, right? So here we only have process to process edge, and there's an arrow from PI to PJ if PI is requesting for a resource and resource is allocated to PJ, right? So in the state diagram, if P is asking for a resource which is allocated to P2, then we have edge from P1 to P2, right? Which says that P1 is waiting for P2. P1 is essentially waiting for a resource which is held by P2. Once it's released, it will come back, right? So if you find a cycle in this graph, then you are in deadlock, right? And detection is a O of n squared operation, which is a graph theory way of trying to find cycles in a graph, right? So in the algorithms class, these algorithms you will go through, and any algorithm which is exponential is bad. O of n squared is bad because as you increase n, the time it takes grows exponentially, right? So essentially what you have is, this is the resource allocation graph you had before on the left, right? And you want to change it to the wait for graph. If one process is waiting for a resource which is held by another one, you have an edge. So if you look from P1 to P2, right? Over on the left, P1 is waiting for R1, which is assigned to P2. So we have a straight line going from P1 to P2 on the wait for graph, right? And similarly from P2 to P5, you have a resource R3 that you're waiting for, right? And similarly for P2 to P3, you have a R4 you're waiting for, right? So the top ones are fairly straightforward. The bottom one, right, R5 is allocated to P4, right? Both P2 and P3 is waiting for R5. So you have two edges, right? P2 is waiting for P4 and P3 is waiting for P4 through R5, right? Does that make sense? So essentially when you take that graph and do the wait for graph, and you see there's a deadlock because there are two cycles, right? And so these two processes, the processes in this graph are in a deadlock, right? And it only works for one instance of any particular resource, right? So if you have multiple resources, then you run something very similar to your banker's algorithm, right? And the essential part is you run the same kind of the same way as the banker's algorithm in terms of what requests you had, what was allocated to you, and stuff. And if you can't find a safe way out, right? So right now this is all the allocation which happened, which was already allocated. So if there's no safe way out, then you're in deadlock, right? And so the algorithm basically goes to the thing. It takes the same amount of time, O of n squared m, right? It takes the same amount of time, but essentially the algorithm here is very similar to your banker's algorithm, right? If there's no possible way out of where you are, then you're in deadlock. Okay. Or here you're trying to find the little opposite way. You say, is there any possible way out? If it is, then you're in safe state. If there's no such state, then you're in deadlock. Okay. So I'm not going to go through the same example. So yeah, there's another example of the stuff. So again you have the allocation and what you're requesting and what is available, right? So you have a request, the sequence P0, P2, P3, P1, P4, right? If you run that, all of them can finish, right? So if all of them can finish, then they're not in deadlock state. If no such sequence existed, then there's no way you can finish from the state where you are, right? Assuming that all the processes were to finish and release the resources, you still can't finish, right? So you'll be in deadlock. So in this case, you can reclaim resources, but you won't be able to finish, right? And that's why you're in deadlock state. So the answer we have to answer is, how often do we have to run this algorithm, right? Which is what we asked before. You have to run it often, right? You have to run it at least how often you expect the deadlocks to happen. So if you run it at every time a resource is allocated, then you will never enter deadlock state, and your system will be excruciatingly slow because you are running a very expensive operation every single time. So you can choose to run it every so often, right? And depending on what your attitude is towards deadlock, if your attitude is deadlock happens, I kill the processes and I move forward, then you can run it every so often. If you never want to get into deadlock state, you have to run it at every allocation. So depending on what you're trying to do, you run it at different intervals. So if you run it at arbitrary times, then it's possible that you're already in a deadlock state, then you have to deal with it, right? So the easiest way to deal with that is to abort processes, kill processes, and that will release all the resources that they have, and you can move forward, right? And you can think of other ways to make this happen. Kill less important processes, kill important processes which haven't run for a while, and so on and so forth, right? All of them you can imagine have their pluses and minuses, right? Essentially, you have a process which is running halfway through. It's made some progress. It's in the middle of doing something, and you are trying to kill the stuff and taking the resources away, right? So it may or may not be acceptable to the end users, right? So if you imagine a resource being like a printout, and half your printout is printed, and your process was killed, right? Then rarely is part of the results useful, and you have some inconsistent state, right? Inconsistent printouts, inconsistent stuff you have. So you can try a whole bunch of heuristics on which process to kill, and that's that, right? So if you have a transactional model, then deadlocks are a little bit easier to deal with. If you have a transactional model, right, when you enter into a deadlock, then I can basically unroll the transaction, right? Because remember, when you're doing a transaction, it keeps all the state of operations we have done so far, right? So I roll back using the transactions to some known state, and then maybe try from there, right? And depending on how well I can go back to a previous state, we may be able to get out of deadlock, right? So anytime it happens, I basically stop the processes and roll them back to some safe state and let them go forward, right? So if you keep doing this, the process may itself not know that this is happening, right? They'll start because they're not making progress, right? But essentially, you make the transaction go forward, and then it rolls back, and then tries to let it run again. And if you get into deadlock again, it detects it and lets you go back, and so on. Sometimes it'll work because there may be other ways that you get into unsafe state, but go back to the safe state. Sometimes this does not happen, right? So, and again, you have starvation because it keeps. So if you are in a point where deadlock is the only option, then it basically goes back and forth. It goes to deadlock, rolls back to some state, then tries to go forward, comes back to deadlock, kind of thing, right? So you can try these solutions, and at the least, hopefully that tells you why most operating systems that you deal with don't deal with deadlocks, right? It's all very expensive because you run all this stuff, and even if you run all this stuff, unless you run it at every allocation, right, you'll still get into deadlock. And if you run into every allocation and the system slows down tremendously, right, you'll still get into deadlock. And if you run into every allocation and the system slows down tremendously, it's usually not acceptable, right? So they don't even try to do anything, they just let it go. If deadlock happens, just reboot the machine and you're good to go, right? So I took a few minutes later. So if the deadlocks